Thank you. Hi, everyone. So today I'm here to tell you about least hit density, which is a new technique to improve key value cache hit rates. This is joint work with Nathan Beckman from CMU and Hashan Chen from University of Pennsylvania, who's here today as well. So key value caches are, in my opinion, a hot area because they're a really crucial layer in modern web applications. So the typical kind of architecture of web applications is you have a web server, and when you're looking for an object, you first go look at the you first query the cache, which typically sits at a separate cluster, usually in DRAM, something like Memcached. And if the object isn't in the cache, then you would go to a slower, persistent database. And the reason caches are important is because they're simply much, much faster than the underlying database. And so for that reason, because there's something like a 2 order of magnitude difference typically between the cache and the database, even small improvements in the key value cache hit rate can have an outsized difference in end-to-end application performance. So an example here from Facebook cluster that runs at a relatively high cache hit rate, 98%. If we can take that hit rate and increase it by just 1%, we would get a 35% end-to-end speed up. And so that's kind of why optimizing key value cache hit rate is important. Unfortunately, choosing the right eviction policy in general in caches is hard, and in particular in key value caches is even harder. So key value caches have unique challenges. First, they have highly variable object sizes. You might have 64-byte objects sitting alongside 64 kilobyte objects, and you have highly variable workloads on the same cache. And so prior eviction policies are typically heuristics that use some kind of a combination of recency and frequency. But these policies usually don't have a strong kind of theoretical foundation, and they usually require hand tuning, which means that they're fragile to workload changes. And to convince you of that, last year's ATC Best Paper Award from Karl Waldsberger et al. Was actually a system that simulates dozens of different cache eviction policies and parameters on different workloads, and for each workload chooses a different eviction policy and parameter because there wasn't just one that worked across workloads. Now, of course, a system like that is great, but it's complex and has high overhead. And so our goal in this paper is to create an eviction policy that can auto-tune itself for any workload. And so in order to do that, let's take a step back and first understand kind of what's the big picture of key value caches. So first of all, our goal is going to be to maximize total hit rate. In this talk, I'll focus on maximizing total hit rate. You can also maximize, for example, per byte hit rate. Our constraint is going to be the limited cache space. So that's, let's say, DRAM on your Memcached server. Uncertainty, when an object comes in, you don't know when it's going to be accessed again. And an added difficulty is that, as I said, objects have variable sizes. So in order to understand how to design such an eviction policy, let's use kind of a simple model here, where on the y-axis, we look at the space that each object occupies. And on the x-axis, you see the time. And let's run a very simple trace where each object here is denoted by A, B, etc. And so at time 0, let's say that cache starts with these 3 objects, objects X, Y, and B. Each one of them has a different size. And then at time 1, a new object comes in, object A, so the cache decides to allocate space for object A. And now let's say a new object comes in and it's object B. And great, object B already is in the cache, so we have a hit. So what we'll do is we'll mark the box, the area of object B in green. And since the cache decides to keep caching object B after a hit, we'll draw a new box for object B, or anytime an object is either hit or evicted. And we'll extend the box for objects A, Y, and X. And now let's say a new object comes in. Again, it's object B. Great. So we have another hit. We'll draw that again in green. And then extend the boxes. And now a new object comes, and it's object A. And so we'll mark the entire area of that A occupied in green. Now, fortunately, there's a new object in the cache, but this object doesn't exist in the cache, so that's a cache miss. And this object is relatively large, so the cache decides to evict 2 objects in order to make space for it. So object C comes in, and the cache decides to evict object B and Y. And so we'll mark the space of B and Y in red when there's an eviction. Okay? And so we can use this same approach and just extend it to the end of the trace. And now let's see, for this example, where did our cache space go? So each green box is equal to 1 hit, right? And each red box is equal to 0 hits because it was a miss. And so intuitively, our goal here is within this kind of space-time continuum is to fit as many green boxes as we can. This is almost like a real estate problem, right? So each box here costs resources, which is its area, and that area is simply, proportional to the size of the object times the time it's spent in the cache. So the size here is the y-axis, and the time it's spent in the cache is the x-axis. And so this leads us to the key idea behind our paper, which is hit density. So we devised this new metric for a cache eviction that combines the probability that an object is going to be hit and its expected cost. So hit density is equal to, in the numerator, the object's hit probability, which is basically a probability that it's going to be green. And the denominator is the object size, which is known, times the expected lifetime, which is the time, the length of the box I showed you in the previous diagram, or it's the time the object will spend until it's either hit or evicted. And so the idea behind this metric is we'll always try to evict the object with the least hit density, or the smallest hit density. But the question is, how do we actually compute or predict these quantities? So let's say we want to estimate kind of the hit density for an object that we know nothing about. So we'll use a metric called age, which is the number of accesses since the object was last requested. And we'll specify 2 random variables. So h is going to be the hit age, which is the probability that the object is going to be hit exactly after 100 accesses, at the 101th axis. And L is going to be the lifetime, and that is similarly just going to be the probability that an object either hits or is evicted exactly after 100 accesses. So again, if we want to estimate kind of the hit density for an object that we, again, know nothing about, we would simply compute the formula below. So that would be, the sum over kind of from 1 to infinity of all the ages of the hit age. That would give us, that would sum up to the hit probability. And then the denominator would just be, the size, which is known to us, time the expectation of lifetime, which would just be, computing the expectation of L. Now, of course, in practice, we actually do know some information about objects, and so it's really easy to keep track, for example, of how long they've been in the cache since the last access. So we can use that information to better estimate the hit density. And so we use conditional probabilities in practice to estimate hit density. And so the way we do that is we monitor the distribution of H and L online. So we have a graph that looks something like this, where in the x-axis we have age, and the y-axis we track kind of the hit probability for each age. And then let's say we have an object, and we track its age. So we know its age is equal to A. Okay? So de facto, if we know that it has already survived until the age of A, we know that it hasn't been hit previously, right? So we can actually discard kind of the graph up to the point of its age, and we can only look, and when we're calculating, for example, its hit probability, we only look at events of ages older than this object. And so then if we want to compute the hit probability, given that we know that it has an age A, we just do the sum, we just start the sum from A until infinity. And similarly, for the expected remaining lifetime, we only look at the lifetime after older than this age. So again, we sum from A until infinity here. Okay, so let me now give you an example so you kind of understand how this works in practice. So I'll choose kind of a workload that is particularly difficult for typical key value caches. So in this workload, we have a combination of common media, which is accessed periodically. So for example, every time a page is loaded, there's some template that is always accessed at a predictable time. And then there's some user-specific objects that have some kind of popularity metric. Okay? And so if you were just kind of to hand design an eviction policy for this workload, what you'd probably do is you'd cache all the common media, and then whatever space you have left in your cache, you would try to use that for the popular user-specific objects. And so the way we model this workload is for the kind of the common media, we just model it as a scan, which means that all objects are referenced exactly when they reach a certain age. So there's a peak. So in this graph here, the y-axis is the reference probability and the x-axis is age. So for the scan or the common media objects, they just get access at a predictable age. There's a peak. And then for the user-specific objects, they just follow kind of a typical Zipfian model, where the older objects are less likely to be accessed. And now let's see how LHD would perform on a workload like this. So obviously, there's this peak here. So let's kind of look at what happens before the peak and after the peak. So for objects, so let's say I have an object and it has an age that's lower than the peak. So I know that the peak is in my future. So that means that this object would have high hit probability because it has this peak. Now, in terms of the lifetime, actually the closer the object gets to the peak, or in other words, the older the object is up to the peak, its lifetime, its remaining lifetime is actually going to decrease. So overall, the hit density in this region of the graph before the peak is actually very large and increasing. Now, after you cross the peak, then, from the conditional probability, you know that this object de facto cannot be part of the common media, and it has to be a user-specific object. And so now you're in a zone generally with very low hit probability. And as the object ages, it's less likely to be hit. And so therefore, you're in a zone of the graph where the hit density is small and decreasing. So this is how the LHD is going to look like. So again, it's going to have this small increase up to the peak, then it drops precipitously, and then it decreases over time. And so this is actually exactly kind of what you would want your eviction policy to do, right? You want it to really guard kind of the objects up to the peak, and even prefer objects that are slightly older so that they have time to reach the peak. And then after the peak, you want the eviction policy to perform something like LRU, where it prefers the newer objects. And so LHD kind of automatically implements this hand-tuned policy. Now, the nice thing about using conditional probabilities is we can incorporate additional features into the ranking function. So in the paper, we actually incorporate two other features. We incorporated, which app accesses an object, and we also incorporated specifically, has this object in the past, how long has it taken it to hit? And we found that both of these features even further increase the hit ratios of the policy, and they can be applied kind of automatically. Now let's see how LHD performs. So we compared LHD to 4 eviction policies. So LRU, so this graph shows miss rate, so the lower is better, and the x-axis is the amount of memory we dedicate to the cache. And so LRU is kind of the worst performing one because it doesn't take into account object sizes. And then we compared against 3 other size-aware policies, adapt size, GDSF, and hyperbolic. And you can see that LHD kind of outperforms them. And this is on an MSR storage graph. And it turns out that LHD works really well across a bunch of different workloads. So the one on the top left is kind of a Memcached as a service workload, and the other ones are all workloads, again, from MSR storage. Another interesting thing about this is you could see that for the different workloads, besides LHD, which kind of outperforms them, different workloads perform better different eviction policies perform better in different workloads. So that shows you that there isn't just one eviction policy that rules them all. In addition to that, in terms of the amount of space we need to achieve the same hit rate, so LHD actually consumes, if you want to achieve a certain hit rate, LHD would consume a lot less space than existing eviction policies. So the blue line here is LHD on the left, and then the other eviction policies are kind of how much more space you would need to achieve the same hit rate. So this is also a way to significantly reduce your server and storage costs. So the remaining time in the talk, I'll quickly kind of describe how we actually implemented LHD in practice in a system which is called RankCache that kind of translates this eviction policy into a key value store. So the general problem is that prior kind of complex policies require generally complex data structures. And complex data structures typically lead to synchronization, which leads to poor scalability and throughput. And so something like GDSF, for example, requires O of log n heaps, which is prohibitively expensive. And even O of 1 LRU is sometimes too slow because of synchronization, which is why many key value systems have actually approximated LRU even further with something like Clock or FIFO. And so the question is, can we achieve similar throughput with LHD? And so our system RankCache kind of makes LHD fast using four main mechanisms. So first, we approximate information. So for example, in order to keep track of ages, we use coarse granularities. The second is we pre-compute the hit density as a table, so we don't need to do it online. Third, we randomly sample objects when we're looking for a victim, so we don't find the actual global the object with the global least hit density. And then we also tolerate rare race conditions in order not to do global synchronization. So now let me guide you through how we do evictions in real time. So let's say there was a miss in the cache and we need to decide which object to evict. So we first of all take a sample of the objects, and then we look up their kind of pre-computed hit density. So in this case, for example, object E has the lowest hit density, and then we decide to evict E. Now, notice that throughout this process, we didn't have to do any global synchronization, which leads to kind of great scalability. Now, in the case where we have a rare race condition, we just repeat this process again and try again. So now let's see how we do in terms of throughput. So we compare ourselves against 4 other policies. So first of all, random, which is kind of the blue line, then clock, LRU, which is represented as a linked list, and GDSF, which is represented as a priority queue. We also further optimize RankCache, which is the purple line, with the red line, which is RankCache plus tags, which is an optimization I won't have time to talk about. And we compare it against 2 graphs. So the one on the right is with 100% hit ratio, where the x-axis is threads, the y-axis is throughput, and the left is 90% hit ratio. So first of all, what you can see here is that LRU and GDSF actually scale very poorly, again, because they rely on global synchronization. And then random does really well, which is not surprising, but unfortunately, in terms of its eviction, in terms of its hit rate, of course, random does really poorly, so that's usually not a policy you want to use in practice for a cache. And then clock is interesting because it does very well when you have 100% hit ratio, but when you go to 90% hit ratio, it kind of stops scaling at some point. And the reason is because clock kind of synchronizes on the hand object. So if there's a lot of evictions, you'll have to kind of serialize them because of the hand object. And what you can see here is that RankCache scales for both 100% hit ratio and 90% hit ratio. In terms of related work, broadly speaking, there's a lot of related work in eviction policies. But broadly speaking, we're inspired from some work done in CPU caches about using conditional probabilities to calculate, eviction ranks. But this is a very different environment than CPU caches. We have variable object sizes, which really influences kind of our ranking function, a lot of points of our design. And then, of course, there's a lot of prior replacement policies in general, but generally speaking, they're typically heuristic-based and require either hand-tuning parameters or simulations. Just the last thing I wanted to talk about is that just in terms of future directions. So LHD is a general framework. It can also be applied in areas beyond key value caches. And even within key value caches, there's a lot of interesting directions. So one thing you can do with this is dynamically optimize between latency and bandwidth. So for example, if you want to dynamically switch between optimizing the hit ratio and the bit-byte hit ratio. Another thing we can take into account is, certain applications would access multiple objects at the same time, so we can incorporate those cross correlations when computing LHD. And finally, there's a lot of caches that incorporate several tiers of storage, for example, DRAM and flash or DRAM and NVM. And so you can use an approach like LHD to optimize data placement when you have multi-tiered storage. So with that, thank you. Happy to take questions.
Questions? And if you don't get the chocolate now, you can take it at the end of the session. Okay.
I hope speakers get chocolates too.
Yeah, from Twitter. I actually worked on cache for a number of years, and the one funny bit is we actually default to random for reasons we can take offline. So my question is this. So in practice, what I have observed is that caches are often not exactly provisioned to the size, the minimum size that's effective, right? There's over-provisioning, and there's traffic patterns, which means certain portion of the traffic is really not cacheable, while the rest is. Have you done any study on real-time traffic, like what is the floor or ceiling, depending how you look at it, and basically the improvement in algorithm versus over-provisioning, what's the relationship between these two options?
Yeah, so I think generally with caches, as you probably know, there is this difficulty in deciding, what's the right metric to optimize for. So are you trying to reduce costs, or are you trying to achieve a certain hit rate, and given that hit rate, reduce your overall cost, et cetera. So I think the idea behind this is the reason I showed both kind of the hit rate improvement graphs and the cost graphs is if you want to have a certain hit rate and then optimize the cost based on that, then you can do that. But if you want to just reduce maximize overall hit rate, then you can do that as well. And I could take offline, but there's various mechanisms to actually fix either of those metrics. So, but thank you.
Hi, Shujia from UT Austin. So can you comment on how often do you need to recompute the hit density?
Yeah, so I believe we recompute every, I believe like 1 million accesses. Generally the downside of this approach, to be upfront, is you do need pretty rich kind of traces. So if you have a very sparse trace, then obviously your statistics will be less rich and you will make less optimal decisions. But so yeah, that's.
A follow-up question is: do you recompute the hit density based on Argo or based on like the access history of your cache?
Based on the access history of the cache. Yeah.
Thank you.
Asaf, great talk as usual. I'm asking this question only for another chocolate, but
we're all here for the chocolate.
So I think most of the slides when you talked about hit rates and the focus was so much on variable object sizes, the first question that comes to my mind is we used to talk about hit rates exactly when all objects were of the same size for a very specific reason, that they were directly correlated, or you could have a direct mapping to the user perceived performance in terms of throughput. If all objects are of the same sizes, 1% hit rate, reduction in hit rate, 100x lower secondary storage, 2x reduction in throughput. When objects are of different sizes, I can't wrap my head around what does hit rate even mean? Why should I care about hit rates?
Right. So hit rate still means latency. So in latency bounded applications, that's kind of so I think that's the main way folks think about hit rate when object sizes are variable. But I agree. I mean, a lot of the models we have break down both in terms of resource sharing and in terms of eviction policies and multi-tenancy when you have objects of variable sizes. So yeah.
Let's thank the speaker.